Ladies and gentlemen, welcome to ICEM 2021. Our sponsor talk will begin shortly. Please be advised to stand by. Ladies and gentlemen, we are honored to have Mr. Simon Fong, Territory Sales Manager of Oxford Instruments Asylum Research in this sponsor talk. Mr. Simon Fong is representing Novatech Scientific to deliver a talk on AFM for piezoelectric and energy storage materials. If you have any questions, please send your questions to the presenter via the Q&A function in Zoom or the comment function in YouTube. All questions will be addressed by the end of the presentation. Please welcome Mr. Simon Fong, and I would like to remind Mr. Simon Fong to watch the Q&A function in the Zoom chat to check for any questions that might come from the viewers. Thank you very much.
Thank you for the introduction. Just let me switch it on. I hope you all can hear me clearly. Yeah. Good afternoon, everyone. Before I begin, I would like to take this opportunity, of course, to thank the organizers for hosting this conference, and also to our distributors, which is Novatech Scientific. I understand this is probably your lunchtime, but I want to appreciate and thank everyone who chose to attend this session today. I really hope from this session, it will be beneficial to you and helpful for your research. Let me first introduce myself. My name is Simon. I'm the Territory Sales Manager for Oxford Instruments Asylum Research. I've been in this AFM field for more than 8 years now. And today I'm going to give a talk on the topic of using AFM for the study of piezoelectric materials and also energy storage materials. And to be honest, both of these piezoelectric and energy storage topic is a very big topic in the AFM community. We might not be able to go very deep in each of these topics today, but I hope it can at least help you understand what is AFM and how it can help you in your research. Okay. Before we dive straight into the topic, of course, let me take you a quick introduction to who Oxford Instruments and Asylum Research is, and some of the fundamentals for those who are new to AFM. So Oxford Instruments has already a history of innovation for over 60 years. Under the Oxford Instruments company, we have many business units, which carries the state-of-the-art of nanotechnology tool in the present day. These business units, of course, includes Andor for high-performance scientific cameras. We have NanoAnalysis, which is a business deals with EDS, like EBS and WDS solution. I think most of you might be familiar with if you are using any of the electron microscope with EBS attachment, so you might hear about us. Asylum Research is us who deals with the AFM, plasma tech for etching and deposition technologies, nanoscience for cryo solutions, magnetic resonance for NMR, X-ray technology for X-ray tubes and systems, and of course our latest acquisition on WeTech, who focuses a lot on Raman technology. So Asylum Research was founded back in April 1999. We have a photo of our 3 founders here, Dick, Roger, and also Jason. In December 2012, we joined the big family of Oxford Instruments. And on the right side here is a photo actually of our new office. We just relocated 2 weeks, I think 3 to 4 weeks ago, because we need to expand our AFM production capability. So we need to move to a bigger site and a bigger space. And this is where we are located right now in Goleta, Santa Barbara. Of course, aside from the headquarters in Santa Barbara, we also have offices all around the world for sales and support. And of course, aside from these offices, we also work together with many of the local distributors in respective countries, especially in Southeast Asia. So as from Malaysia, Singapore, and Indonesia, we are represented by Novatech Scientific. And if you are from this mentioned region, please do not hesitate to contact them directly. You can surely find their contacts from their website or even this conference website. As for anyone outside from these countries, please feel free to contact me. My details are stated in this slide. So it's you can drop me an email at simon.fong@oxinc.com. Sorry, simon.fong, sorry. Yeah. Asylum Research has always been the leader in AFM innovation. If you were to take a look at the history of AFMs, she always sets the innovation standards for in the AFM communities. For example, we are the first ones who sold digital controller for AFMs. we are one of the pioneers to develop closed-loop scanners for AFM using our patented these LVDT sensors, which is short for linear voltage differential transformer. One of our earliest innovation is also the multi-frequency technique called the bimodal mode. It's basically a mode which we drive the cantilever at 2 resonance frequencies. And it's also the base for a lot of the modes which we develop much later on. So for PFM, piezo response force microscopy, this is actually an AFM technique which allows us to study the piezo properties of the material. So this is one of the research fields which we really excel in, and we are the leader in this community for more than 15 years. Okay. One of the unique techniques in PFM that we have developed is called the dual resonance dual AC resonance tracking mode, which is DART in short. And we'll discuss this a little bit more in detail later. Okay. There are other AFM techniques which we pioneered, like in nanomechanical and analytical modes, which I will not go into details. And of course, one of our most powerful innovation is basically the blue dry photothermal excitation, or in short, it's called blue dry tapping. This is indeed a piece of technology which brings us a leap forward on how it improves tapping mode imaging. We have 3 product family in ICEM research, if you have not heard before. So we have the MFP 3D, which is one of our most versatile and affordable AFM product line. This is a very comprehensive model. If you and your team would like to explore researches in many directions, in material science, in life science, or even in both. Okay, so BioAFM, our BioAFM product line is also under this MFP 3D. Cypher, the second one, Cypher is our flagship and our best-selling model. One of the key highlights for Cypher is the exceptional performance in ultra-high resolution imaging. Okay, I will have some images to show you later. And of course, Jupiter XR is one of our largest large sample stage AFM, and the performance is following the footsteps of the Cypher. So Jupiter's capability in imaging is uncontested. Many of the large sample stage AFM in the market actually cannot perform at Jupiter's, at the level of Jupiter. I'm unsure if everyone is familiar with AFM, but for the benefits for those who are new, I have prepared following the following slides to briefly explain the fundamentals of AFM. So let's just take a quick look. So what is an AFM? AFM stands for atomic force microscope, or atomic force microscopy. AFM is a type of visualization tool, and it's a type of microscope. Yes, but AFM is a little bit different because it does not use light. It does not use electrons to image your sample, but it uses a mechanical probe, okay, like a tip here, okay, and it touches it physically and image your sample. Okay. Just imagine the situation in the photo on the right. Bottom right here, you are using your finger to touch your surface. You feel the feature, swiping your finger left and right. At some point, you can probably imagine how the surface actually looks like without actually seeing it with your eyes. This is the same for an AFM. So the AFM is capable of imaging your sample and measuring in 3 axes, X, Y, and Z, where Z is the height or thickness of the step of the sample, and Z is uncommon for an SCM or TEM or even a light microscope to obtain. So this is where AFM can actually excel. You can measure that Z, the thickness or the height of the sample. This slide shows a schematic diagram of a typical AFM. As illustrated previously, we use a mechanical probe, or we call it a cantilever. Okay. If you can see at the bottom right here, it shows actually how small the probe or cantilever is. Okay, it normally comes with a box of 10. The size is around 3 mm, the body. Okay, and then at the end of the body, there's actually a lever which extended out of it. At the end of the lever is where we can see the tip, and this is where actually it touches physically with the sample. So the typical radius of this tip is around 10 nanometers. The cantilever is made of flexible material. When we push the cantilever onto the sample, the cantilever bends. Okay, and the bending is measured by an optical level detection system, consists of a laser diode and also a photodetector system. Okay, so in order to get an imaging, we need to, of course, move the sample or the probe. Okay, and we can move that using what we call a scanner. So in X, Y, and also Z directions. Okay, and of course with a feedback mechanism system which is not listed here. The signals are collected, then processed by an instrument called a controller. Basically, it is the brain, considered as a brain of the AFM. Here shows you a few examples of images captured using an AFM. All of these images are topography, which means in AFM term, we call it height image or height channel. Like the electron microscope, AFM does not capture color information. So what you see here is basically pseudo color. And the color always represents some kind of information in AFM. So in these cases, when we talk about height image, so this color actually represents the height of the sample. Okay, and normally you can actually read this from a little scale bar at the side of the image when you get an image, of course, with the AFM. The other examples of is in human hair and also the insect wing. At the bottom row is basically also height images, but at a higher resolution. Okay, AFM can be used to image not just material samples, but it can also be used to image biological samples. As shown here, we have a DNA image, a very high resolution DNA image, where we can see the grooves in the DNA. We can also use AFM to image biological cells like fibroblasts, cancer cells, bacteria, viruses, tissues, and whatnot. Okay, and of course, at the bottom right here is a graphene sheet of graphene sheet. You can actually also measure the thickness of the graphene if you draw a profile line over the image. Aside from being able to image topography, AFM can actually do so much more. One of the unique features that is different from the electron microscope, the light microscope, is its capability to physically touch the sample. Okay. By physically touching the sample, we can obtain many other additional information, such as the mechanical properties, thermal properties, and even electrical properties. Okay. Just like our fingers, if you can imagine, like in the earlier slides, when you touch on a surface, you can basically feel whether the surface is soft or hard, cold or hot. And sometimes if you are dealing with electrical instruments, you might feel sometimes electricity or statics if you are not careful. So aside from being a visualization tool, AFM can also be a material characterization tool. So what can AFM characterize? These are actually just a few to list out. So in mechanical properties, you can probably get some stiffness or Young's modulus, adhesion forces. In electrical properties, you can get current or conductivity, measure capacitance, magnetic field, electric field, surface potential, piezoelectric coefficient, of course, for piezoelectric properties. We can measure thermal properties like thermal conductivity. And of course, there are also one which is the electrochemical properties, which we commonly use for energy storage materials. Here's another two examples just to show you. The first one on the left is basically the color here shows the conductivity or the current flowing through the sample. So the red color shows a higher current value, and the blue color here shows a lower current value. Okay, this color is actually overlaid on the topography, and in that case, you can actually correlate between the topography and also the conductivity of the samples. This is one of the things that you can do. On the right side here shows an example of a three polymer blend. We have the polyethylene, polystyrene, and so polypropylene. The color here shows something different, and it shows a Young's modulus instead of the current or conductivity. So Young's modulus is basically the stiffness of the material. As you can see here, polystyrene is the yellow color, which has the highest stiffness, and then comes polypropylene, orange color, and then the lowest stiffness is polyethylene. Okay. So these are the few things you can measure. Of course, you can correlate again using the AFM. Aside from the many characterization, there are also external accessories that can help to expand your research capabilities. This includes, of course, environmental control, where you can heat or cool your samples. There are also specific seal cells, which allows you to do liquid exchange or even gas exchange environment, especially for energy storage materials and battery, because you need, of course, the environment to be moisture and air free. So you need to fill with some inert gas like the argon gas. So you can do that with the AFM. There are also other accessories which helps you, like the external magnetic field. If you're doing magnetic studies, there are also stretching stage called the nanorag, and of course our imaging technique called the blue drive, which I'll explain in the next slide. Okay, so it's a little bit of explanation to what is blue drive. So in conventional tapping mode, as you can see here, it is what is tapping mode, how it is done. So basically tap across the sample. And this tapping is actually generated by a shake piezo. So a current will pass through a piezo piece, and the piezo will actuate the cantilever attached to it to a resonance frequency. However, in a real case scenario, this shake piezo does not only shake the cantilever, but also other parts of instruments is attached to it. This includes the probe holder, some debris, even the environment surrounding the cantilever. Okay. As a result, unwanted responses will appear in the tuning process, and this will affect your interactions between the cantilever tip and the sample. Ultimately, in your image, you'll see some sort of artifacts, or maybe you can get some noisy images, and even you can don't see what you want to see basically on your sample. So what is blue drive? Blue drive is basically replacing that shake piezo with a blue laser shining at the base of the cantilever. And then by modulating the laser power, we can actually actuate the cantilever to a resonance frequency. Okay. The sole purpose of blue drive is just to actuate the cantilever so that we get a simple and clean response. So when we get a simple and clean response, we get a stable cantilever dynamics. And what it means here is basically it generates, it produces higher resolution images, stable imaging in liquid. It preserves the tip lifetime, and of course, faster scanning rate. Here's one of the benefits of blue drive. It allows you to capture ultra high resolution images and data of your sample. Blue drive can work in both air and also liquid environment. There are actually a lot more benefits of blue drive, but due to the time, limited time that we have, I might not be able to explain everything. But if you are interested to know more, please feel free to contact me or even to contact our distributors. Then we can actually have a short discussion about this. That goes a little basics on AFM. Let's move on to the next topic of AFM for piezoelectric materials. Okay. The application for piezoelectric materials of actually very wide. The applications, of course, include sonar, ultrasonic, and medical imaging, sensors, actuators, energy harvesting technologies. Even in the realm of electronic devices, we have in RF filters and in surface acoustic wave devices. These advancements requires the ability to image and quantify these piezoelectric properties in a nanometer and even molecular scales. So ultimately, this of course has led to the development of using AFM as a tool to do this local and nanoscale imaging, spectroscopy, and even up to the manipulation of piezoelectric and ferroelectric materials. But before that, of course, what is piezoelectric material and what is PFM for those who are still new? So piezoelectric material is basically a type of material that generates voltage when a mechanical stress or pressure being applied to it. As you can show in this little cartoon here. Okay. Inversely, okay, if we apply a voltage to this piezo material, the material will then actually expand and contract. So it is working in both ways. PFM stands for piezo response force microscopy. It is actually an AFM technique for you to detect this kind of piezo response of the sample by displaying it displaying as an image and then induced by the applied voltage. Okay. So you can see. Let me just click this video for you to show. So you can see that by applying an AC voltage to the sample, so the sample will expand and contract, and that changes is actually detected by the probe or the cantilever. What kind of information can you measure with the PFM? So there are two main information. The first one is called the amplitude. So amplitude is basically refers to how much the sample expands and contracts with respect to the voltage being applied to the sample. Okay, we can use this amplitude to actually characterize the piezoelectric coefficient, or which we call the D33, by using this this equation. Okay, that's the first thing you can actually measure with the PFM. The second thing is called the phase. It's a little bit difficult to explain, so I will skip the explanation part because it's not needed to understand the remaining slide. But what you need to know is that this phase helps you to identify the polar directions or the domain polarization of a material. Okay, so let's look at an example. Okay, this is actually a periodical pole lithium niobate sample. Okay, and here the image shows actually a cross section which has down domains and up domains. Okay, and also with the domain walls, domain boundaries, that you can see that. Okay, and then you see at the let's switch to the right side, the PFM phase. Okay, So you can clearly see that there are two shades of color here, purple and also the white yellow. Okay, this shows actually there are two different phases, and this represents actually two domains, which one represents the up domain and the other one as the down domain. Okay, and there is the use of the PFM phase basically, as I explained earlier. On the left side, we have the PFM amplitude image. What I want to explain is basically these dark lines, the boundaries here is clearly seen, which is actually the domain walls. The reason because of this is because when we scan at the domain wall, the piezo response from the adjacent domains actually cancel out with each other. Therefore, the motion or the amplitude at this domain wall is actually very small, and it's very low, basically at the lowest value where you can measure at the amplitude image. PFM signals and amplitudes are generally very small and hard to measure. Okay, if you look at this table, most piezoelectric materials, okay, the D2 or the piezoelectric coefficient is actually in the order of few picometers per volt. And looking back at the equation here, if we were to apply a 1 volt, the deformation would just be a few picometers. Okay, so to give you an illustration, how small is 1 picometer? If you look at this dot, this is 1 picometer, and at the right side here is basically an image of a carbon atom. So even though AFM is a very sensitive instrument, it is still difficult for AFM to measure such small measurement in a scale of few picometers. So what can we do to amplify and improve the PFM signal and amplitude so that we get a better image and better results? Okay, one of the easiest way to do that, of course, through this equation again, is to increase the tip voltage or the voltage applied to the sample or whatever. Okay. Again, when you increase the tip voltage, basically you increase the amplitude, so you get better signals. However, this is sometimes not very feasible when we have a very thin sample and a very sensitive sample. So applying large voltage will basically cause polarization state to change, and of course, sometimes in the worst cases, it's actually wreck or damage your samples. So this is one of the ways. Of course, this is still one of the ways to do that. The second way, of course, to do it is through a phenomenon called the contact resonance. It happens. It's basically when the AC voltage frequency is the same as the resonance frequency of the system, which means when the tip is in touch with the sample. Okay. However, this method is only reliable when you have a sample which is really flat, and the contact resonance frequency will be affected if the topography is not flat or if the tip degrades. Okay. So based on these two choices given, of course, to protect your sample to get better signals, I think contact resonance would be a better way to do it, a better choice in comparison with raising the tip voltage. Okay. So in order to resolve these problems in contact resonance, we can actually resolve them by tracking the contact resonance frequency. So we use this technique, what we call the dual AC resonance tracking, or DART. Okay. In short, in summary, what DART does is basically it applies two voltages on the probe at the same time. We apply two AC voltages at the same time on the same probe, but with a slightly different frequency. Okay. Whenever the contact resonance of the sample and the tip in the sample actually changes, these two frequencies from the DART will actually detect the shift and correlate it back to the right resonance frequency. Okay. On the right side here is actually an example. You can see a conventional with the tip, with only changing the tip voltage. You can still get the phase, but it's a little bit noisy. With the conventional contact resonance image, you get a good signal, but again, you get instability in the imaging. But combining these both with DART, you get a clear and sharp image and best good signals, and also clear domain images. So that is basically the golden method for the go-to for AFM. Just to quickly explain this, this is actually an experiment, a case study of done on a BTO. These domains were actually imaged with PFM decreasing in temperature over 2 hours. So as you can see from the video here, we can detect the changes of the PFM amplitude and the phase changes when the temperature reaches to a certain level. Here's a here's another combination of technique between PFM and conductive AFM. What the researchers wanted to do is basically to control the conductance of the material through polarization. Okay, so on a certain polarization state, the charge domain wall actually closes and inhibits the current passing through, and the other state, it opens up the domain walls and it allows the conductive AFM, the conductance to increase by 1000%. So this is what the researcher is actually doing. So I have to rush through these few slides because I still have a little bit more on this battery storage material. Okay. So yeah, just to quickly do an overview, there are a lot of course, studies on energy storage material, but one of the things I want to focus on is basically the battery, especially for lithium batteries. Okay, and there are some experimental conditions that you need to consider when you conduct this battery research. Of course, first of all, and many of the energy storage materials are very sensitive to moisture and to air, and require some sort of stringent control. So one of the ways to achieve that, of course, is to put the AFM into a glove box. And of course, not all AFM can do well in a glove box because there's a pump running, there are some, you have to use the gloves, which is very not user-friendly. But using our Cypher ES system, our performance is actually guaranteed. And at the same time, our user-friendliness is still there actually. All the alignments are actually automated and you don't have to do it manually. Okay. On the right side is basically an image to show you that it's possible. There's no trade-off for the performance because that we are using the Cypher ES and it fits, works with the air pump working as well. Sorry, yeah. Oh, so the other important thing, of course, for in-situ experiment for battery, you are required to assemble all these parts into a small little battery and then to measure. So you can actually do it with what we call electrochemistry cell. And this video and also the right side example is basically demonstrating how you can do this. This is actually a standard crystal formation of a copper grown and then stripped away by a gold electrode. So you can actually do that inside this electrochemical setup. Just quickly going through this example. So there are a lot of experiments you can do with this electrochemistry cell and also this Cypher ES system, because this is one of the using the zinc. Basically, this is researchers trying to find trying to see the effect of these overpotentials at different values and how it affects the zinc growth and changing the film thickness and of course the roughness as well. So this is what the experiment does. And this is one very interesting experiment on a more sensitive material, which is the lithium and also oxygen sample. All these things actually assemble into this little electrochemical. This diagram actually shows electrochemical stage, and then you have all these battery parts of anode, cathode, electrolyte separators, current collectors, and whatnot. Okay, and of course, on the right here shows you the charging and discharging experiment. So during the discharging part, you can see that there is actually some solid electrolyte interface going on the sample, which is shown as this red and yellow bulb. Okay, and when during the charging phase, this actually disappears completely when it reaches 50% of the state of charge. So basically, this shows you a highly cyclable kind of process, and this can be used to study, of course, many of your battery materials. So thank you again. This marks the end of my presentation. I think I took a little bit 2 more minutes of the time. Yeah. The last 2 minutes. Yeah. So if you have and I'm not sure we have time for questions Q&A, but I'm surely we can address this later as well.
Okay, thank you very much, Mr. Simon. I think we have one Q&A from the floor. Okay, there's a question asking what type of facet surface are more suitable for AFM analysis?
So I'm not. So I mean, from what I understand, the question is what kind of surface is suitable for AFM analysis? Is that what you're trying to say? So so basically, AFM actually used for more kind of like a flat surface, a smooth surface kind of sample. So the roughness measurement of us runs from few, of course, can run from picometers to up to microns. But of course, there is also a limitation to, because with measuring roughness, you have to measure the height. So the height is actually limited by the Z scanners most of the time. And the Z scanner have a maximum probably around 9 microns. So you cannot go more than that. So if you are measuring, to measure using the AFM analysis, probably it has something to do with some flat samples of the height, which is lesser, probably less than a few microns. That would be perfect for AFM. I hope that answers the question.
Okay, thank you very much, Mr. Simon, for your insightful talk and sharing on the Oxford instrument. I think if you have any further more questions, we will collect and we'll divert to you.
Thank you. Yeah.
Thank you very much for your time.
Have a good day.
Everyone. Yes, now we'll pass back the floor